Welcome to Math 22B of Harvard College. I'm Oliver. You see me here in my office. I have several cameras, we can look around. I'm from Switzerland. This video is about just introducing myself, and I will also introduce our TFs and course assistants in class. So I'm Oliver. From Switzerland. You see here the place where I grew up. It's the Rhine Falls, beautiful waterfall in Switzerland. First of all, you should look at the syllabus. It's on the website. So there's a two-page summary with the most important information about, what happens when, so what are the grades, etc. First of all, everything is also on the website. The website is public. The grades are always important. We have just 2 midterms, each 20%. Then they are done in class. Then there is a homework, 20%, 10% proof. So there are actually 3 components in the homework. So for every lecture, so we have 2 lectures per week, which are regular multivariable calculus stuff, and then 1 lecture proof part, and we have a final comprehensive 3-hour exam. So we have a regular homework every class. There are 5 problems. At the end, we will discard the 3 least homework scores. So, and the homework is due weekly. Planning to do the exams in class, and also the 3-hour exam will be in person. So we have quite a good support in calculus courses. We have problem sessions, office hours, we have this proof part. So all of this, you should see this just as resources. Come and go at any time, which are times which are available. We try to spread this out over the week. So proofs are a beautiful thing. It's established that something is true, and so there's some beauty in understanding an argument and see why it is true, and not just have to rely on experts telling you what is true. So that's the beauty of mathematics. And we try to keep this light and entertaining also, and every week we have a different topic. Like the first week we talk about what is a theorem, what is a definition, what is an induction proof. So there's every week there will be some theme. You don't need a book. So I have many calculus books. If you look here, I have also at home I have a library. But most of these calculus books are now you can find the information also online. If I would have to select out one book which is close to this course, it's Master and Tromba. I have the 6th edition. I don't know whether there's another edition, but it has a mathematical maturity. I know both authors, at least Master when he was still alive, and so they are good mathematicians, and they have done a nice book. But you can also live without the book. About the first week, so we are going back in time, actually very, very much back in time, because we are looking at Pythagoras' theorem. And this has started already much earlier. The Babylonian mathematicians already looked at Pythagorean triangles. And this has been known at the time of where this eternal story run. But space is very exciting. So we actually explore space, but not the linear space like in linear algebra, but beautiful geometric objects appear. This is my favorite object in maybe the YouTube star. It's the Mandelbrot set, which is a 3-dimensional Mandelbrot set. But it needs a lot of, I like this because it needs a lot of computing and a lot of knowledge to make such a movie, and to look at that object. And it's also a complete mystery. We don't know what is actually happening with this object, whether it's connected, for example, or not. But it also relates to coordinate systems. Here, these are coordinate systems in space, which actually is here spherical coordinate systems. And coordinate systems have been introduced by René Descartes. So you see him here teaching calculus and geometry to Queen Christina. He was a giant both in philosophy and mathematics. Also Pythagoras, the Pythagoreans, So the Pythagoras theorem, which says that if this is A and this is B, this is C, that A squared plus B squared is equal to C squared. It's a very beautiful identity. Pythagoras and also other cultures, like in China, one has also kind of independently got to this. I will show a little movie in class about this. This is a very interesting story. But we will prove this. We will prove this theorem from scratch. So you can also in space, if you have a triangle in space and you have a right angle, so you have still the same identity. Three-dimensional space is really our domain where we mostly work, but we will also work, of course, in 2 dimensions. We will also work in higher dimensions. And we will address higher dimensional spaces with matrices, like vectors. So a vector, for example, 1, 4, 7, 3. This is a vector in R4. So this is a vector. And so we also look at matrices in general. So 3, 4, 2, 6, 2, 0, 5. And that would be then a 2 times 4 matrix. And the vector is just, so in this case it is a 4 times 1 matrix, which is a 4 vector. I might think, why do we talk about 4 dimensions and why do we talk about higher dimensions? But you can also look at this as data, and when you have data, they are usually high dimensional data. And if you look at computer vision, I have a couple of books here in computer vision. So computer vision books are all essentially calculus or linear algebra, and also dealing with deal with higher dimensions. Like if you want to understand perspective, for example, then you have to work already in 4 dimensions. So, so the Greek mathematicians have done a lot of mathematics already, like Archimedes. We will see a lot of, Archimedes in this course. The first who was getting the volume of the sphere, trying to duplicate the famous Escher picture here. So with a sphere. So just a little bit of pep talk. Math is everywhere, so I'm a big fan. It's also eternal. I just saw the movie Eternals. That's eternity comes in, and it's really something. If you have established a mathematical truth, then it is true for all eternity. And we have explored microcosmos with mathematics, like the elementary particles, atoms and molecules. We have also looked at the stars and the universe, black holes now, and all kind of exciting objects. We are using mathematics, using actually the mathematics we learn here. Now, of course, the mesoscale is very, very hot. Yeah, if you look at that, there's a lot of computer vision. There's a lot of 3D graphics, augmented reality. I actually kind of use this a little bit, kind of in a primitive way, augmented reality. If you have a surface, for example, I can look at the surface here, and I can display it here. And of course, it's not done in real time. I have to afterwards to plant this surface in, and but that will in the future, I'm pretty sure I can actually talk here and then present here this surface. Another story. Yesterday I was visiting the glass flowers here at Harvard. It's actually close to the place where we have class. These surfaces is all made of glass, kind of replicates of plants or of sea creatures. When the curator, I told the curator that I'm a math teacher, and that we actually have, we are using computer algebra to generate some things, and actually we have done some projects where we have done flowers, built flowers, etc., using topics of using surfaces. At that time, this was done with glass. It's just unbelievable what this Blaschke father and son could do for Harvard. They were hired to do that for Harvard, and that's their table or working table. The working table of us today is, first of all, the mind. It's also the computer, and we can paint and build things using computers, but we can also build them real and do 3D printed versions of it. Also students have done that. Use Google Earth. You can place things now in Google Earth, and then you can fly around, like I was here planting the Riemann zeta function, which is a famous function of two variables, which is believed to have roots on a line. Nobody knows that. It's $1 million problem. But you can also just look at the graph, and you can fly around in Harvard, or you can build the Mandelbrot set, and you can plant it in the Boston Harbor, and then you can fly around. There's a lot of beauty. I think even simple surfaces can be beautiful, like culture all over the world. People have contributed to mathematics, and there's a lot of gossip also. And so we see here actually a couple of mathematicians who are associated with calculus. Mathematics is a pure science. This is a famous XKCD joke, but it's true. It is the hardest and the most pure science, but it has many applications. Waves on surfaces, and they behave in a complicated way. Maybe I just end with a little metaphor. I was also passing by the divinity school, and they have a puzzle maze. So it's actually not a maze, it's a labyrinth. Labyrinth is a special maze where you have no choice, you are not branching. But so you can ask yourself, what does this have to do with, say, our course 22B? Now it turns out that there's a lot of connections. So, and the question is, you have to go from part A to part B. Of course, this is very easy here. In this case, you find a path. It's very easy to get here. How many mazes are there? So what is the total number of mazes? Now, of course, divergence and gradient in this finite setting have to be defined differently, but they are exactly in one-to-one correspondence what you have in calculus. What we do, we learn about the gradient, we learn about the divergence in this course. The Stokes theorem, that will be one of the highlights of the course, the generalization of the fundamental theorem of calculus.